All right, ladies and gentlemen, this is going to be the next video on radioactivity. So let's get started on this next video. So nuclear reactions. Well, a nuclear reaction, the release of radioactivity, is really just spontaneously emitted radiation. Now, particles are going to do this naturally on their own if they're an isotope that is unstable. And when we're talking about nuclear reactions, well, this is a reaction that involves a change in the atom's nucleus. So we can release energy by breaking bonds, but we can also release energy by breaking apart the protons and neutrons within the nucleus. So if we look here in this image, we're shooting a neutron. We are hitting uranium-235 and we are breaking it apart. So it's going to release neutrons and we're separating it into barium and krypton. So by doing this, we can see we're going to get two new atoms because now we change the number of protons and we're also going to get this massive release of energy. So when we're looking at types of radiation, well, we're going to release different types of radiation dependent upon the reaction. So we have alpha radiation, which is when an alpha particle, which contains two protons and two neutrons, is released from the nucleus. So we went from radium to radon, and we released an alpha particle. Now, alpha particles are going to have a positive 2 charge, and we're going to talk about why and how we came up with this. Now, beta radiation is a little bit different. Beta radiation is simply the ejection of an electron with a -1 charge. So in this case, we're going from carbon-14, and now we're going to nitrogen-14, and we're releasing a beta particle. Lastly, we have gamma radiation. And gamma radiation is really just high energy radiation that has no mass, and it's really just the ejection of high energy. So if we're going from uranium, we're releasing an alpha particle. So we're going from uranium to thorium. We're releasing an alpha particle, which is 2 protons and 2 neutrons, but we're also releasing gamma radiation or gamma rays, which is just pure energy. Now, alpha radiation has the least amount of energy, then beta radiation is somewhere in the middle, and gamma radiation is super high in energy. And this is what we're really talking about when we talk about nuclear reactions and nuclear bombs. This is the one that goes through and releases a massive amount of energy into the environment. Now, when we're talking about this radiation, the reason that these reactions are occurring is nuclear stability. And the primary factor in determining an atom's stability is the ratio of neutrons to protons. So if we're looking at this, some isotopes are naturally unstable and they eject particles to achieve this stability. We're artificially doing this when we have a nuclear reactor in a nuclear power plant. We're trying to go through and artificially get these nuclei to rip apart and release energy in the process. So the way we figured out the charges is we had a lead block with a radioactive source, and we ejected radiation through this hole, through this other lead block. And we had a positive plate up at the top, and we had a negative plate up at the bottom. Let me go through and just erase this a little bit so you can see this. Go back to the pen. So we have a positive plate here and a negative plate here. Now, we figured out the charge of the beta particles because they were attracted to the other end of the positive plate. And we could see the trajectory of the beta particle. It came up here, splattered on this side of the zinc sulfide coated screen. And we looked at the alpha particles, and as we ran it through positive to negative plating here, it was attracted to the negative plate. And it splatters here on this part of the screen. Now, we knew that gamma rays had no charge because we ejected them through, and gamma radiation went through and came in contact with our zinc sulfide here, but was not affected by the plates. So because of the actual curvature, we can go through and see that we have a positive 2 charge and a negative charge here based on where they ended up on the zinc sulfide coated screen. So what we can see here is a virtual nuclear reactor, and we are going to go into the reactor chamber. So what we're doing is we're going into the water pool where the rods or the pellets are going to be contained, and we're actually going to go through and shrink ourselves down into the atomic level. So right now we're going to the bottom of the reactor core, continuing to delve into the pool, and now we're going to shrink ourselves down to the atomic level to look at the uranium pellets here. So now if we look at these uranium pellets, what we can see is if we shrink ourselves down a little bit further, the actual reaction taking place. So what we're going to do is travel along these rods, and these are going to either contain uranium-235 or plutonium. Generally, we modern nuclear power plants are going to use uranium. But if we're looking at an atom here, what we're going to do in this reaction is shoot a neutron at it. Now, at the center of this atom, we have our cloud here, and we see the electron cloud. We're going to take this neutron, and we're going to go through and shoot it at the nucleus of the atom. When that happens, it causes it to split. Again, when we're going from uranium, now we're going to krypton and we're going to barium, and there's also going to be this massive release of energy into the water. Now, this energy is going to exist as heat. So we're going to go through, continue to release this energy, continue to go through and cause explosions within these nuclei. And when this happens, it's releasing heat into the water. Now, that heat is going to travel through a duct system. So now we're going to transfer that heat through this duct system out of the reactor core. And as we go through and take it out of the reactor core, it's going to travel through piping, and it's going to spin the turbine. So as we're watching the heated water go through the duct, this is superheated water, we're going to go through, vaporize it, turn it into steam, and then this steam is going to go through and then spin a turbine, and that turbine is then going to power an electric generator, which powers the nuclear power plant. That's how we're getting the electricity out of the nuclear power plant. So you can see the turbines here going through and spinning. As we can see the particles moving through, we can see the turbines going from left to right. That steam is powering that turbine, which is hooked up to the electric generator. And then that steam is condensed in the big towers that you see in the nuclear power plant. And then from there, it goes and is released into the atmosphere.